Lastly, let's talk about the osmotic pressure. That's something you probably have not heard of before. This is a unique type of pressure. It is not a pressure that the solution exerts, but another thing like the vapor pressure or the boiling point, where if the pressure is equal to the osmotic pressure, something happens. Okay, so every solution has its own osmotic pressure, and the way we define an osmotic pressure is we put, let's say we have salt water or something like that, okay? And I have water here, and I have salt water here, okay? And I put a membrane here that can only, is semi-permeable. It can only take the water. The salt can't go through. The salt gets stuck. So the water can go between here or here, okay? According to laws of diffusion, the water will want to go from here to dilute this. And it will. The pressure I need to put on this to stop it from happening, that's known as the vapor pressure. And is designated as pi, capital Pi, and is equal to I, which we saw before, times the molarity, times the gas constant, times the temperature, absolute temperature. So let's see this in action. Let's say I want to know the molarity of a solution of glucose containing glucose having this osmotic pressure, and applying the osmotic pressure formula, which is the Van 't Hoff relation. This is it. Okay. This is given to us as 0.00542 atm. Glucose doesn't dissociate, it's just 1. That's what I'm looking for. R, I'm going to use R as 0.08206 liters atmosphere mole Kelvin. And my temperature is 4 degrees Celsius, which is 277 Kelvin. Okay, so I could just put it all in. And which is equal to 4 degrees Celsius. I can put it all in, and once I do that, I get that my molarity is equal to 1.50 times 10 to the minus 4th molar.